Hi everyone, my name is Madison Swain Bowden. My pronouns are she, her. As Ben mentioned, I'm the diversity chair for this year, and thanks to Ben and Eliza for that wonderful introduction to our conference. I'm really excited to introduce our first speaker for this weekend, Brett Cannon. Many of you know him, but in case you didn't, Brett Cannon is a Python core developer for over 19 years, a member of the Python Steering Council for now, and the software engineering manager in charge of the Python experience for VS Code. Brett has cats with his wife, Andrea, who thinks scikit-learn is awesome. Take it away, Brett.
Thank you. All right. All right. Well, good morning, everybody. As Madison said, my name is Brett. I work at Microsoft. Quick thank you to them for letting me come. And we're going to talk about Python syntactic sugar. And I got a little extra time, so I'll try to go nice and slow. But I will say there will be a link at the end of this talk to a whole bunch of blog posts where I ramble about this topic extensively. So don't feel bad if you don't pick up on something. It's all written down somewhere else. So you'll have a second opportunity to listen to me in your own head about what the hell I'm about to talk about. But to start off, I should probably answer, what the heck is syntactic sugar? And it's actually a little hard to define, but probably the best definition I've come up in my head is you can think of it as a piece of syntax that you don't actually need. And what I mean by that is it's a piece of syntax where you could actually probably accomplish the exact same thing and end up with the same results, but potentially in a much worse way. If that makes sense? So think of it as if you didn't have it, your life wouldn't end, but it might not be quite as good as if you had it. Hopefully that makes sense. I'll obviously have some examples on a couple slides, but once again, just think about it as some syntax where if it's there, it makes your life better, but if it wasn't there, you could still, through a very roundabout way, end up with the exact same result with the exact same semantics. What I'll say is the reason I did this whole project to try to figure out what exactly Python syntactic sugar was I was trying to kind of distill down what is like the fundamental bits that Python couldn't exist without, right? Like what's its core? As a little side note, this is actually to figure out what it would take to re-implement all of Python in WebAssembly, which I have not done. But that's kind of where this kind of all came from. Now, I should specify exactly how I set up my rules for myself for what was or was not considered syntactic sugar for this project, which took 2.5 years. So good pandemic-sized project. I targeted 3.8 because this all started back when 3.8 was the new hotness, which shows you how long I've been working on this. 3.12 will be coming out in beta in May, by the way. I required for myself that I had to be able to do single whole file analysis, but not entire application analysis. So what I mean by that is I should be able to take a PY file, right, analyze it, potentially strip out a bunch of syntax, insert some other code that does basically the same thing in the end, but I couldn't look at other files to get the same, to kind of figure out the results, right? So I couldn't necessarily change how a function operated based on how some other stuff in another module worked, if that makes sense. So self-contained in a file, but it wasn't only per line or anything like that. I also said that some dynamic stuff could be odd. So what that means is if you called the locals function, right? I was okay if you saw some funky little things in there. Basically because Python already does that. For fun, if you ever do a list comprehension and have it return locals, you'll find there's a little funky little variable in there that you didn't know existed that's storing the list as it's being created. So little Easter egg there. But basically I just said, you know what, if there's a weird little variable you didn't know about, it's okay. And then basically I finally said, if a built-in function could do something, it was okay if I could do that through a function as well, right? Like if the interpreter had to be able to do something at a fundamental level, it was okay if I created a new function to do that. You can call that cheating if you want, that's fine. I'll show you an example later where you could choose to disagree with me on that one, but that's essentially the rules I try to follow for myself to decide what was or was not Python's actual syntax. And it turns out there's only 11. And the reason I start the talk this way is because I actually managed to get rid of 83 other pieces of syntax. So it's way easier to go through 11 than 83 different things. Okay, So what are those 11 key pieces that we seemingly, at least based on what I could figure out, I'm not perfect, by the way. I might actually be wrong on some of these. What could we actually not live without in the end? Well, first of all, integers. And the reason this is you kind of need a baseline object type that can represent all kinds of data, right? So if you think about it, you can represent floats via integers, right? It's the mantissa and the exponent, right? So a float is really some number to the power of some other number multiplied by some number to move that decimal point, right? So you can actually fake it with integers. Complex numbers, exact same thing, right? The real part, the imaginary part. Bytes. What happens when you index into a byte? You get back an integer. Same thing here, right? So all the fundamental types that are not like collections, you can actually represent as an integer. So I had to have some baseline to be able to do that. Function calls. Can't really fake that. If you can, let me know, but I couldn't figure out a good way to not have function calls work in terms of actually be able to call something. As I said, because I set that rule that you couldn't span across files, there was no way to kind of unroll things to kind of fake function calls. So for that, I couldn't get rid of it. While, okay. You kind of have to have something that can do loops, and you need something that can have a conditional. So one really convenient thing here with while is you get both for the price of one, right? So I'll show later how you can use while to actually fake an if statement, but you can also use while to fake a for loop, right? So with that one piece of syntax, you kind of get two things covered for one thing. So that's why while is there. Try and accept. This is there because once again, because I couldn't look outside of a file, I couldn't unroll anything to kind of fake ways to return an exception, right? Like if you happen to be familiar with Rust, and it's okay if you're not, in Rust you can return a result, which is either okay, everything went well, or oops, there was an error, right? So you could theoretically do that in Python as well, but because they said I couldn't cross functions, or cross files, sorry, I couldn't do that. So I had to keep exceptions around in order for it to work. Now, the key point here is you can fake finally, you can actually unravel that, and else as well. So the key thing here is try and accept is the critical part, but all the other parts to a try statement are actually optional. Def. If you're going to be able to call functions, you kind of need a way to write them. Kind of straightforward. And in those functions, you need a way to return, unless every single function you write returns none, which that would be an interesting program, but probably not very useful. For those of you who don't know, by the way, obviously, Python returns none by default if you don't say anything. So theoretically, as I said, you could get rid of it somehow, but otherwise you kind of need a way to actually get that returned. Yield. Yeah, there's no way to just pause code in the middle of something, at least that I know of. Once again, because I couldn't unroll things, I kind of needed a way to have generators still work, so I kind of needed to keep yield around. Assignments. This one, based on the next two examples, theoretically, I might be able to get rid of somehow, but honestly, after 2.5 years, I had to stop somewhere. So the next two pieces of syntax I think will tie into this a bit more, but basically I couldn't figure out a way to control namespaces such that you could just ditch assignment, right? Because in case you don't know, pretty much all of Python's namespaces excuse me, are dictionaries under the hood, right? So you would think that maybe somehow I could unroll it and just have a dictionary that represented all the namespaces, right? And somehow you just write to a dictionary. But the reason I don't think I could get rid of that and thus had to keep the assignment is, one is globals. I might be able to get rid of this one if I thought really hard and was willing to get a headache over it, but I decided not to go that route. Basically, this is here because you could end up writing a nested function within a nested function and have to write out to the global and all that stuff. There might be a way to use import to import yourself and then get at the dictionary for the module and then write directly to that. So I think there might be a way to get rid of it. But honestly, that's not enough to get rid of assignment because of nonlocal. This gets way trickier because now you have nested closures that lead to different scoping, and it's way harder to control which scope you're going to write to. So for me, my money is I can't get rid of that, and that's why I need to keep assignment in the end. Global, maybe, but I'm not going to worry about it. If you figure it out, let me know, though. And then finally, del. The reason this is here is two reasons. One is, depending on the semantics you have for your interpreter, forcing cleanup immediately, it's hard to fake. The other thing, which is technically implementation details, so be nice to PyPy and pretend it actually does not happen immediately. And then the other thing is raising a name error dynamically is a little hard to get right if you don't go through that if statement that does the del. You got to keep track of everything, and it gets really messy really fast. So I decided to throw my hands up and say, I can't figure it out, and let it go. But that's it. That's basically the three pieces of syntax that you need to implement all the rest of Python. So import, classes, plus everything, assuming I didn't screw up. And for those of you who might know what a Turing machine is, this is basically a Turing machine with some Python flourishes. Now, if you don't happen to know what a Turing machine is, it's not a big deal. It's kind of the theoretical definition of a computer from Alan Turing, and basically it just says a computer can be imagined as a thing that can read data, write data, process data, and make decisions about data. That's basically it. And if you think about it, we have all that, right? Like, we have assignment, right? We have function calls to be able to read stuff, assignment for write, function calls also, and def to process the data, and then we have while to make decisions about it, right? Same with try and accept. So all the fundamental bits you need to be able to do all those fundamental bits of programming are all there in those 11 pieces. And then everything else could be built using these actual pieces. Hopefully that makes sense. I saw at least one head nod yes, so they just answered for the room. Thank you. Okay. Let's see here. So now we're going to start going into examples. I'm going to, because as I said, there's 83 individual pieces of syntax I managed to get rid of. I can't go through all 83. I only got 25 minutes, and I don't think you want me talking 5 seconds per one. So I'm going to go through 4 examples that kind of give a flavor of how this works, so that if you're at all like me and your mind's going, how the heck do you do this? And you want to sit there during the conference to try to figure something out. At least you'll have some tools to think about it, and also to kind of give an idea of how some things work behind the hood, especially for CPython. So we're going to go through 4 examples here. The first one is a very simple one, and might be a little surprising that it's the simplest one, but we'll do it. One thing to mention, there is some color on this slide. It is entirely optional, so if you're colorblind, do not worry about it. It's just there to help those who can see the red in the letters as things transition, but don't worry about it. Okay, x.y, attribute access. How do you unravel that? How do you change that from that to something with only uses those 11 other pieces of syntax that I just defined? I'll give you a couple seconds just to think about it. Give myself a chance to drink some water. Okay, so it's just getAttr, right? So it literally is a built-in that we already have that you might not think of, but every time you use that .dat to access something, it's literally just getAttr. If you actually look at the bytecode in CPython, it's calling getAttr under the hood, right? It's nothing fancy. It's just way nicer to write. Like, as I said earlier, syntactic sugar is something that you could have accomplished another way, but it's just nicer to actually have it, right? So if we didn't have attribute access using DOS, you just write a ton of getAttrs in your code. It wouldn't be pretty, but it still worked exactly the same, and you get the exact same results in the end. So, nice and simple. Unfortunately, they're not all that simple. And part of that is because the language definition can make things somewhat interesting, in somewhat surprising ways, too. I will fully admit, I've been a core developer for nearly 20 years. It'll be 20 years next month. And I still found stuff about the language that I didn't even know about. So you'll be surprised what we kind of promise you in the language. So as an example, decorators. How do you think this unrolls? And don't feel bad if you don't get this, because I didn't know how this fundamentally worked under the hood, and I helped implement it. So It's okay. There's a tweak in the language spec that you might not be aware of. But I'll give you all a couple seconds to think about how you might implement this, and then show you the potential surprise. Okay. I'm going to assume everyone who's thought about it's going to think about it. So, it's a little weird. And the reason is the language definition specifically says that the bound name that you're decorating is not set until all the decorators are called. Right? I had no clue that was a rule. And it makes sense when you stop and think about it, right? You don't want someone to get access to something you're in the middle of decorating. Right? You don't want to say, oh, look, I can get a hold of Y right now somehow, and oh, but it's not done being decorated, and then something else, right? So it totally makes sense, but it's something that's not intuitive if you just think about how generally the semantics basically work. So this is just one of those cases where there's a lot of little subtle stuff to it all that you kind of have to pay weird attention to. So in this case, I just use a temporary variable. Once again, as I said, dynamic stuff might be a little odd, right? Like, you can check the whole file to make sure there is no underscore y variable to make sure you're not going to clash with anything. But as I said, if you called locals or globals, there'd be a weird little case that you might come across like, what the heck is that? But this still ends up with the right semantics, right? You call the decorator, y is not bound anywhere yet, so you don't have that weird little bit, and then it ends up including y in the end. And that's basically how decorators work, right? It still matches your mental model, but the technicalities of it are a little funky, as it were. Now, special methods. This might be more what people are used to when they think about syntactic sugar, right? Like, how do we implement stuff like plus and minus and that kind of thing? I'm going to start off with a smaller example, but the key thing here is when you think of special methods, you might know of them as magic methods, or dunder methods, you know, underscore, plus, or add, sorry, underscore, that kind of thing. That's what I mean when I say special methods. If you read the language spec, we refer to them as special methods, so I'm just going to use that term, but magic method, same thing, dunder method, same thing. Now, sorry if it's a little small, but this is going to expand out to a lot of stuff horizontally. So if you can't read it, it says tilde x. All right, invert of x. What do you think that converts to? Once again, might be a little surprise for you if you don't know how all this works underneath it. Don't worry about the name of the method, honestly. You can forget the special method name. Just think about fundamentally how this case would probably turn out. And as I said, there might be a trick that you weren't aware of about how this works. Okay, so that's what it becomes. So there's two bits here that might be a bit surprising. One is that you call type on the object, and that's what you use to get the method from. And the other one is you explicitly pass x in. I'll explain why you call type on x in a second. But for any of you who've ever wondered why the heck am I always made to type self out, this helps explain why, right? In this case, x, which would normally have just been self, the way you're thinking, is actually now an explicit argument to the method. So there's a reason why we ask you to always type self out on methods, is because you do occasionally actually explicitly pass in that argument. It's not a magical little thing like this in some languages where somehow it magically appears. Sometimes you actually explicitly pass it in. Now, here's the question. Why are we doing it off the type? Which, by the way, in this case, it would just return the class. So like if x was an integer, for instance, it would just return int, right? So why are we doing that? Well, if you think about how CPython works, it actually makes a lot of sense because there's a massive performance boost you get from doing it this way. So it's okay if you don't know C. This is a line of C. I'll explain it real quick. But basically, if you look, that PyType call, that's a macro. So at the C level, all objects in Python are basically a big struct, which you can think of as a data class, basically, right? And in there, there's a attribute that basically says what's your type is. Dunder class, if you look at a Python object, basically is that, okay? So PyType is just going to get that attribute. Now, the thing is at the C level, this is really fast, right? There's no like, this is not like looking something up in a dictionary, right? This is literally just a memory offset to C. So it's really, really fast, okay? So we do that, okay? So that thing is gonna give us a class. Classes at the C level have a big struct that define a bunch of pointers to functions and stuff. One of those is called TP as number, which stands as type as number. So if a type, such as int, is a number, it will define that struct. Okay, perfect, okay. In there, there's something called NB invert, right? Which is number invert. So it's a function that knows how to invert a number. Get that thing out, okay? That's now a function at the C level that takes one argument, in this case x, right? And we just say, okay, invert this integer for me. And it returns it. Done, okay? So, really fast, really fast, really fast, call the thing with the thing I'm working with. That's very fast at the C level specification. Now, imagine if we were actually getting this off of x itself. Well, we have to look that up now in a dictionary, right? Remember, everything in Python is a dictionary, kind of for ease of implementation and understanding, and allows us, honestly, to make dictionaries as fast as possible and get a lot of wins off that way. But the key thing there is looking anything up in a dictionary, if we're doing like x.dunder invert, right? If you're doing it the way you might have thought about this, that dictionary lookup already is way slower than that right there, right? So by doing it this way, we're able to guarantee a certain level of performance by saying, no, at the C level, we're just going to just do a bunch of dereferences on some structs and get stuff way, way, way faster. So that's why you always, for all this stuff, you always take the type of the thing you're working on, get the function, and call it fundamentally at the Python level. So it leads all to the same when you actually write it out, but at least the interpreter can kind of realize that this is how it's going to work out, and just do it that way. Binary operators. So this is probably what most of you are familiar with when you think of syntactic sugar, right? Like plus is actually a bunch of method calls, but how does that all function at the fundamental syntactic level and actually kind of at a semantic level? Well, let's start with x minus y, okay? Getting a little tight on time, so I'm going to give you a little bit of time to think about this, not a ton, but just think about what you think this might devolve into. Okay, so some of you may have thought it devolved into getting the type of x, calling dunder sub for subtract, and then pass in x and y. And you'd be right, like that is one of the steps. As you can tell from my foreshadowing, there's some more steps. For instance, let's think about it this way. What happens if x doesn't define dunder sub, right? Like for instance, with plus, there is no order precedent. There's no concern about order, right? As long as one of them has it, that's all I really care about. So what happens if x didn't actually define dunder sub? Well, we have r sub, which basically stands for right-hand side sub, right? So in this case, what you can say is, well, if the left-hand side of a binary operation doesn't know what to do, let's ask the right-hand side. Maybe it knows. But because you have to care about the order, we have the R version of all these things, R add, R sub, R molt, et cetera, to be able to say like, hey, you're on the right side of this binary operation. Do you know how to handle this case? Now, there's another wrinkle to all this, and that's what if you do have like a dunder sub, or maybe even a dunder R sub, and you just don't happen to know how to deal with the other side, right? So like let's say it's, I don't know, string minus int, right? String won't know how to handle that, but it does define, it might define something if it happened to know how to work with that. Or actually, sorry, way better example. Stir times whatever, right? Like stir defines multiplication, but only works with integers, right? What happens if you pass in a float? What happens? Well, what happens is the implementation will turn not implemented. But to be clear, this is not too many nots. This is not implemented error, right? That exception. This is the not implemented object. And what happens is when you return that, it just tells Python, hey, I can't handle this case. I need to just move on and just let it go. maybe the other side knows how to deal with this, but I personally just don't know how to make this work, right? So if you happen to find your own class that knows how to make string multiply whatever, this gives that side a chance to actually participate and actually make everything work in the end. Now, the key thing here with all this is the R version, the right side version, is only called when the two sides are different, right? So if X and Y are the exact same type, we totally skip this whole check the other side bit, because actually at the C level, there's a chance that dunder sub and dunder R sub are the exact same code. And because of that, there's no point in calling both sides twice with the exact same code, so we just kind of skip that extra call that's going to be completely redundant. So when about this whole R sub stuff, only happens if the types are different. Now, here's another freaking wrinkle that you may not have thought about, is what happens if you are dealing with subclasses. And let's say you have like an integer minus a subclass event that you wrote, right? Like always answers, right? That always returns 42, right? You want to make sure that that gets to participate, and it might have a different result in the end, even though it's on the right-hand side. Once again, you don't get to control necessarily if someone puts you on the left side or the right side as a subclass. But you want to make sure that that subclass gets a chance, because it might want to return a different value than what it itself would have wanted to do. So here's what Python does. It goes up front, okay, are they different types? Yes or no, right? And they are, right? So we're talking about our standard int and our magical int. Are they subclasses of each other? And in our case, we're going to go yes. Okay. Well, do both of them have an R sub version? Yes. Okay. Are they different? Once again, we don't want to run the same code twice, so we don't check. If this is true, then actually we run R sub, dunder R sub, first. Once again, to give that subclass a chance to participate, because otherwise int would get called and go, no, it's just whatever, right? It's a normal thing. But at least with this, our special subclass that always returns the answer 42, because that's the answer to everything, gets a chance to do that and override basically int's default way of doing things. Hopefully that makes sense. Read the blog post for more information. Yeah. Now, you are not meant to read this, but this is to show you this is what subtraction in pretty much any binary operation devolves into. Right? Once again, you don't have to have subtraction, but I bet you want it now that you realize this is what it takes to make it work. Okay. So real quick, because I'm already over time, and luckily I got a little extra time from Eliza and Ben, is sometimes you end up with sugar on top of sugar. So in this example, how do you devolve if? Once again, I'm really short on time, so I'm not going to give you too much. But basically, as I kind of hinted earlier about while, you can use while to fake if. Because really, in the end, it's basically a while loop that's only gone through once if it happens to match. Okay? But notice I used break, and that was not on our list of 11 things. So this can devolve even more. And now that's how you devolve break. Right? So you can use little tricks. You're like, oh, well, you can solve it one way, but then, once again, it's an onion. You can start peeling the layers back and back and back. But at least mentally, it makes sense. But in this case, you might notice I use not and. Not's really easy, so I'm not going to worry about that, but and's kind of tricky. So maybe this doesn't quite work either. So you can devolve this even more and go all the way down to using try and except. And this totally works. You will notice, though, that I kind of cheated with the raise. But as I said earlier, if something in a built-in function needed to be able to do could do something, then I said, fine, I can write a function to do that. If you don't like that rule, you'd have to add raise. But basically, this is how you can totally do if with only while and try except. So that's all of it. I want to give a quick shout out to two people who helped a lot with all this. So first is my wife, Andrea, for proofreading. She's right here. She proofread the vast majority of these 22 blog posts, so she deserves a lot of credit for dealing with a lot of the spelling mistakes, grammar problems, and making sure that everything's clear to everybody. So if you messaged me on Twitter back when I was on it, or on Mastodon saying there's a typo, that's because she didn't proofread it. And then a quick thanks to Guido for being helpful to answer all my random questions when I asked on Python Dev, because, as I said, I learned a bunch of stuff that I didn't know. And also, he proofread the classes blog post, which was complicated. Once again, go read it. So that's the link to my blog, snarky.ca. There's a specific syntactic sugar tag on there that you can go read that has all the blog posts. But if you just go to snarky.ca, you will find my minimum viable Python blog post, which was the final post on this, that specifies kind of the 11 pieces, and it's got the same tag as well, so you can just click on the tag and read it. And that's it. So thank you very much, and have a good conference.